compass. This thing. So it's very annoying to use. There's a lot of errors to it. How it works is it's a disc like that with a magnet placed inside of it, and it's floating in basically a bowl of liquid. And because of that, there's a lot of errors. So the errors that come with it. VD-MONA is the acronym, right? First one is variation. Yeah, well, variation. We have deviation. I guess I can't spell. There we go. Magnetic dip. Oscillation. North, south, turning tendencies. We do this with UNO, so we'll talk about that in a sec. And then acceleration / deceleration. This one's ants. I'll talk about all that in a sec here. So, variation is the difference between magnetic north and true north. So if we look at a sectional here, that's why you zoom in and get the variation lines, which are over, where are they? There it is. Right here, that's the variation line, right? Because if we think of the Earth, the magnet or the compasses point somewhere else. They don't point to the straight North Pole where you think Santa lives, right? They're just off. And it's just every once in a while. You'll see these numbers change very slightly every few months. But that's variation. Going back to this. There we go. Deviation. There are things inside your aircraft that shift your magnetic compass away from its true accurate headings. Radios, anything metal really, or anything electronic causes magnetic field interference. That was really simple. Just pay attention to your magnetic deviation card if you're using the magnetic compass to navigate. Then we have magnetic dip. So magnetic dip is this right here. The closer you are to the north or south pole, it dips towards that side. In the equator, theoretically, you have no dip. More north you go, more south you go, more it looks like that. So magnetic dip is what causes the north-south turning tendencies and also the acceleration-deceleration error. Without dip, those two wouldn't exist. The last one before we go into north-south and acceleration errors is oscillation. So because it's floating in liquid, if you were to fly into turbulence or anything, it just kind of oscillates, vibrates around, kind of distracting, a little annoying, but nothing you can really do about that. All right, so going back to north-south turning tendencies. This, again, caused by magnetic dip, right there, can be corrected for. So this will happen the most when you are turning towards north or south. It doesn't happen at all when you're turning towards east or west. So what I mean by this, and the correction stuff, you correct it by taking half the latitude plus 15. So what we're going to do, we go to our, here we go, hello IFR. These are lines of latitude, right? And the latitude climb like a ladder. There's another one. So here in Phoenix, it's roughly, is that 34? That says 34. We put it right here in Phoenix. You can look at this number, it's 33 something. So we take half of that, that's what, 16 something? Plus 15 again, roughly 31, so we'll call it 30. So this would change depending on where you are on Earth. So if I go to like Seattle, right? Seattle, the latitude should be something like 48, right? Put that over 47, right? So half of, we'll say 48. That's 24 plus 15. That's 39, right? So a big difference. Anyways, back to Phoenix. There we go. What that means is if you're turning to full north or south, you're going to either undershoot or overshoot by 30 degrees, right? Half of 30 plus another 15, 30 degrees. Some scenarios here. If we are turning, we're starting from a, let's say 09 or 090 heading, and we're going to a 360 heading, right? So we're going to turn left. II.A says we undershoot north, overshoot south. So we're turning towards north, so we're going to undershoot here. Because we're turning left, we're going to undershoot by 30 degrees. Meaning that we're going to roll out on a heading of 030. So it's 030. Whereas let's say we start, we can start from anywhere. Let's say we start from 020. Doesn't really matter where we start. And then we make a right turn to heading of 180. It says overshoot south. So you're going to overshoot by 30 degrees. So you're going to roll out on a heading of 210. You can divide this up even more if you want to be more accurate. So here's compass. We know that up here is north, east, south, west. I'm just going to draw like that. Why is it that color? All right, so we know that we correct the most for north and south. 0 for east and west. So we can divide this up even more. So here's 360, here's 0, 3, 0, 0, 6, 0, and then this one's 90, obviously. So here we're going to correct the full 30 degrees, assuming we're still in Phoenix. Here, only 20 degrees. Here, only 10 degrees. And if you're turning to east or west, 0. So let's say we're starting from somewhere heading of, I don't know, 200. Starting with 200, we're going to turn all the way to a heading of 040. So we don't need the full 30 degrees. We'll just do 20. And because it's on the north side, we're going to undershoot it. So undershoot it by 20. We're going to roll out on a heading of 060, assuming we're making a left turn. All right, so that's north-south turning tendencies. Acceleration and deceleration is a lot simpler. Is if you're on an east or westerly heading and you accelerate or decelerate the plane, it's gonna when you accelerate, it's gonna turn towards north. When you decelerate, turn towards the south. It only happens when you're an east or westerly heading. Both of these will be flipped if you're in the southern hemisphere. But we're going to learn from the northern hemisphere, so who knows an ants.